Hey Chris, real quick video here to explain how individual points on the Earth can see the sun above their horizon for more than 12 hours a day, depending on the tilt of the Earth. So I'm going to start with a couple of things. This is what I'm calling the light-dark sphere, right? Which is simply a sphere that is facing the sun, and half the sphere can see the sun above its horizon, and half the sphere cannot. Right? So this is just simply a sphere divided in half, one half showing the dark side, the side away from the sun, and one half showing the side that can see the sun above their horizon. 50-50. We're all in agreement, right? We can agree that that's how it works. So now the thing that I have is I have a second sphere, which I'm going to call the time rotation sphere. And this sphere is simply has a axis of rotation, and it is divided into 24 equal segments, right, 15 degrees apart, and therefore I have 12 hours in half the sphere, so I have 12 hours on half the sphere as it rotates around this axis, and I have the other 12 hours that make up the 24-hour day. I've also included the line at 35.5 degrees, which is the latitude of Oklahoma City, Oklahoma, just as a reference for people that are in the U.S. So we can show that we have, in fact, that is at 35.5 degrees. If I look at this sphere from the front and I grab my protractor tool, I can see that this sphere, the angle from this line, the equator, up to this line, and we look down here, we can see it says approximately 35.5 degrees because I actually typed it in to match this website, which was Oklahoma City, Oklahoma, and 35.4 degrees. So that's where I got that. So that's this plane is the plane that Oklahoma City rotates around the northern hemisphere in a 24-hour day. So when we just take a look and we superimpose one of these on top of the other, right, and we are at the equinox, we can see that we get exactly what we would expect, that in a 12-hour period, I'm in the light for 12 hours and I'm in the darkness for 12 hours, and that applies to every point on the globe. Right? Every point is the same on the equinox. We all have 12 hours of daylight, 12 hours of darkness. So what happens now if I go to the extreme, which would be the summer solstice, where the northern hemisphere tilts toward the sun by 23.5 degrees. So if we just rotate it a little so I can see what I'm doing, and we grab the rotation tool, and we want to rotate around the red axis, and we're going to rotate. I'm going to click there and I'm going to type in 23.5 degrees and hit enter, so you can see down at the bottom that we set an angle of 23.5 degrees, which represents the summer solstice, and I'm tilting toward the sun in the northern hemisphere, right? So we're now at the summer solstice, 23.5 degrees. And now if we superimpose, so this Earth is rotating around this axis like we talked about, exactly at that point. It comes around in 24 hours and it'll be at that point again. And if we look over here, right, it's 12 hours from this point to this point. None of that has changed just because we tilted over 23.5 degrees. The thing that has changed is the plane at which we get this half of the Earth. Every point on this half of the Earth can see the sun above its horizon, right? And the fact that we pulled this hour mark ahead of that point, it means that in Oklahoma City on the summer solstice, right, you can see the sun for about an hour and close to 15 minutes, right? That's an hour block. That's round numbers, a quarter. So at the point here where the sun should be setting, right, I have an extra hour and 15 minutes at the end of the day, and I have an extra hour and 15 minutes at the beginning of the day where the sun rises early, because as we both agreed right up front that every place on this half of the globe can see the sun above its horizon. And if we happen to go back to that website, we can see the sunrise and sunset times for June 21st. Excuse me, the mouse is a little wonky. June 21st, 14 hours and 33 minutes, which is exactly what we see when we model it out on the globe.